So far in physics, we've treated most objects like particles. So we'd have a floor and we'd have a box, we'd apply a force to that box to push it, and we'd imagine we're applying that force at one little place, and we called that a point particle. So imagine we're treating a box as a point particle. What we're going to start doing in Chapter 10 is treating this box as a system of particles. So we're no longer going to use this ideal point particle approximation. And our introduction to this is going to be through the concept of momentum. Momentum is a quantity that describes how fast an object's moving and how big it is. So momentum, which we denote with the letter P, is equal to an object's mass times its velocity. So the units of momentum are going to be the units of mass, which are kilograms, and the units of velocity, which are meters per second. And we leave the units like that. We don't have any special name for this. But where did the concept of momentum come from? To help me remember where momentum actually comes from, I usually like to think about cookies. I think about Fig Newtons, named for the famous physicist Isaac Newton. Newton invented calculus in order to explain motion and come to his 3 laws of motion, the second of which says F is equal to ma. Force is equal to mass times acceleration. And to see where this comes from, and actually to see where Newton got this from, we're going to start with the definition of momentum. P is equal to mass times velocity. As I mentioned, Newton invented the field of calculus partly to explain physics. Calculus is the mathematics of change, of changing quantities, of rates. So I'm going to change this quantity. I'm going to change momentum. So I'm going to take the derivative of momentum, and I'm going to do that with respect to time. If I do that to one side, I have to do it to the other. So I'm going to take the derivative with respect to time of both sides of this equation. I have a mass times a velocity. A derivative of a product has a very specific rule that you have to follow to differentiate it. You have to follow the product rule. So I'm going to use the product rule to find the derivative of mass times velocity, to find the derivative of momentum. I'm going to find dp dt is equal to the first variable, mass, times the derivative of the second variable, dv dt. And since I'm following the product rule, I have to add the second variable, v, times the derivative of the first, dm dt. This is the product rule. It tells us that the derivative of a product is the first times the derivative of the second plus the second times the derivative of the first. Here's where the physics comes in, and we know mass doesn't really change. Mass is a constant. Weight can change, but mass stays the same. Since mass is constant, the change in a mass should be 0. So now we find that dp dt, the derivative of momentum, is equal to mass times dv dt. If we go back to our first couple of chapters, we remember that dv dt, the change in velocity over change in time, is equal to the acceleration. So I now find that dp dt, the derivative of momentum with respect to time, is equal to mass times acceleration. But we know from previous chapters that force is equal to mass times acceleration. So this is how we get Newton's second law in the original way that he stated it. The derivative of momentum with respect to time is equal to force. So a force is really just a change in momentum. Just a quick little aside about how to work with momentum. Let's say we have a bunch of particles. I have a little ball that's going up at an angle, another little ball that's going down at an angle, it has some momentum, and I have a third ball that's going off in another direction. All these momenta are going in different directions. I can add the momenta together. The total momentum with a little vector sign is equal to P1 plus P2 plus P3. Since these are all vectors, I can't just add them. This is a vector sum. So when I'm adding momenta, I need to use the different components. In a vector sum, you need to separate into components. This is the same thing we had to do when we were using forces. When we added forces, we needed the x direction and we needed the y direction. Same thing with momentum. You need the x direction, you need the y direction. So be careful with components of momentum. This is different than last chapter where we were working with energy and didn't have to worry about components. As we continue to learn about momentum, it's important to discuss how it's conserved, the conservation of momentum. We already know about this. We've actually worked with it a little bit in chapter 9. Now, where does it come from? It's a side effect of Newton's laws again, of particularly Newton's third law, which tells us that every force has an equal and opposite force. Well, we know that force now is equal to a change in momentum, is equal to dp dt. So let's say I have two particles, particle 1 moving to the right and particle 2 moving to the left. They each have a momentum, the same size particles traveling at the same speed, so P1 and P2. According to Newton's third law, we're going to have an equal and opposite force acting between these two particles. If the forces are equal and opposite, then the total force inside of the system is going to be 0. Force has to be equal to 0. If the total force is 0, then the change in momentum has to be equal to 0. So what is the side effect of these forces having to sum to 0? Take my momentum 1. P1, if I differentiate it, has to give me force 1. The force of the first ball has to be equal to the derivative of its momentum. Force 2. If I differentiate my second momentum, the momentum of my second ball has to be equal to force 2. Force is the change in momentum. So now if I take my two forces, force 1 plus force 2, I know that these forces are equal and opposite. They add up to give me 0. If that's true, then dp1 dt plus dp2 dt has to add up to give me 0. Again, this is all a consequence of Newton's third law. Every force has an equal and opposite force. If the forces are equal and opposite, they add up to 0. Therefore, the changes in momentum have to add up to 0. So what does this mean? The derivative of a sum being equal to 0. So I know that the sum of my derivatives is equal to 0. The sum of dp1 dt plus dp2 dt is equal to 0. I'm going to rewrite this a little bit differently. The derivative with respect to time of p1 plus p2 gives me the same result, but it's a little more a little bit more tidy. So my question is, what derivative is going to give me 0? If I want the derivative of p1 plus p2 to be equal to 0, that tells me that p1 plus p2 has to be something specific. It has to be a constant. The derivative of a constant is 0. It's the only way you can have a 0 derivative. So what this means is p1 plus p2 is equal to constant. And this leads us to the conservation of momentum. As long as I don't have any other outside forces acting, then the total momentum in a system, in this case we had p1 plus p2, is going to be a constant. It's never going to change. P initially is going to be equal to P final. And this conservation of momentum, remember, came from Newton's third law of motion. And to get some practice with how to solve these types of problems, take a look at problem-solving techniques on page 310 in your book. Final thing to note about momentum is that dp dt, the total momentum inside of a system, is not always going to be equal to 0. If you have external forces acting, if you have something outside that's pushing on your particles, then the derivative of momentum with respect to time is going to be equal to the sum of those external forces. So this is something to keep in mind, and to get some practice with these kinds of ideas, try checkup number 10.1 as we move on to section 10.2, center of mass. In section 10.2, we're going to start thinking about the center of mass, and we're going to think about sizes of objects. We're no longer going to assume that we have a box sitting here and that all the mass is right at the middle. We're going to assume that all the mass is at the center of mass. I like to think about this center of mass as being the balance point of how your mass is distributed. So the general idea of this is that each mass in a body contributes its position by an amount that's scaled by its mass contribution to the entire system. We can write this algebraically, and we can find the position of the center of mass, x of the center of mass of some object, is equal to a bunch of tiny little point particles, maybe one that's mass 1 at a position x1, plus mass 2 at a position x2, plus mass 3 at a position x3, and we can keep going so on and so forth, all divided by the total mass. So the position that I have is scaled by each mass contribution of tiny little particles and where those particles are. So we have this general algebraic equation for finding the center of mass. We can rewrite this in terms of calculus, and this should look familiar. How do we write a sum in calculus? We use an integral. So the position of our center of mass in terms of calculus is going to be equal to 1 divided by the total mass in a system times the integral of x times a bunch of tiny little masses, tiny little point particles. So to review, what are these different pieces? Our dm is an individual piece of mass. It's a little point particle that we're going to use to build up the entire size of our object. Customarily, when we're practically working with this dm, with this little tiny change in mass, we want to remember that dm is equal to the density times the change in volume of a little object. This is going to be a very useful equation, a very useful formula to know. So remember that one. Our x, that's going to be the position of that piece of mass, where my tiny little piece of particle is. Position of a mass. And then finally, our big M out front is the total mass inside of our object. So what does that look like? What are we talking about here? Let's take our usual box that we're used to drawing. We're no longer going to assume all the mass is at the middle. We're going to break it up into tiny little mass segments. Tiny little boxes. Each one of these little boxes is a different mass. Each box that I see here is a different point particle. It has its own little mass. That mass comes from its density times the volume, the size of that little box. The x is the position of that mass relative to some coordinate system. And finally, the total mass is how big this box is as a whole. And I can use this calculus definition to find the center of mass in not only the x direction, but I can use this same equation and just replace your x with a y or a z. And you can see this in your book on page 316. To get some practice with the center of mass, I would suggest looking closely at example number 6 on page 317. What kinds of things can we do with the center of mass? We can find the potential energy. Potential energy of a center of mass is actually pretty easy to find. Let's say I break up my object into a bunch of tiny little objects. So my potential energy is going to be equal to the sum of all the potential energy of those little blocks, the little point particles I separate my object into. m1 times g times the height of the first little particle, plus m2 times g times the height of the second little particle piece, plus ... You get the idea. I can sum up all the individual particles in a body. But that m1 times y1 plus m2 times y2, which I can separate out by factoring out a g, that looks very, very similar to my equation for the center of mass. Looks very much like y of the center of mass is equal to m1 times y1 plus m2 times y2, all divided by the total mass in the system. So by multiplying this big M, the total mass, over, I would find that M times the position of the center of mass is equal to m1 times y1 plus m2 times y2 plus all the other little particles that make up my body, my system. If you look closely, you can see m1 plus y1 plus m2 times y2 is the exact same thing as I've written here, which is all equal to m times y of the center of mass. So my potential energy, if I just substitute this in, is equal to G times M times Y of the center of mass. And what we see here is that all I've done for my normal potential energy equation, potential energy normally is mass times gravity times height. So I've just replaced my height with the position of my center of mass. That's all you have to do for potential energy when you're separating a body into its multiple point particles. Replace your height with the height of the center of mass. So it's kind of like a cheat to treat particles still like point particles, even when you're using the center of mass, when you're treating them not as point particles. To get practice with this, I would suggest looking into Checkup 10.2. Now, we really introduced the concept of momentum at the beginning of the chapter so that we could discuss the motion of a center of mass. We can write an equation for the velocity of the center of mass that looks very similar to the position equation. The velocity of the center of mass is equal to mass 1 times velocity 1 plus mass 2 times velocity 2 plus all the other mass particles that you want to use to make up your system, all divided by the total mass. But if we look at mass 1 v1 plus mass 2 v2, all the masses times all the velocities, this is just the total momentum in your system. So the velocity of a center of mass is equal to the momentum of your system, so we'll call it the total momentum, all divided by the total mass in your system. Very useful to know that velocity of center of mass is the momentum divided by the mass. And I'm going to work with this equation just a little bit more. We're going to first solve this for momentum. That's what we were introduced to in the very beginning of the chapter, so let's go back to that. The momentum in a system is equal to the mass in the system times the velocity of the center of mass. Something we've been doing, we derived Newton's second law. We saw momentum came from Newton's second law by taking the derivative of momentum. So we're going to take a derivative again. dp dt is equal to, and I'm just going to leave my mass here. Mass is constant, so the derivative is 0, times the derivative of the velocity of the center of mass with respect to time. So then my dp dt becomes equal to the mass times the derivative of the velocity of the center of mass, which is just the acceleration of the center of mass. And there's two situations we can have. We can have a situation with no external forces. If there's no external forces, then my dp dt is 0. We can go back to the beginning of the lecture to see that. If I have external forces, then I now have some acceleration, and my dp dt is no longer equal to 0. My dp dt is the mass times the acceleration of the center of mass. So a good quiz question to ask would be, what is the difference between these two situations? What is the acceleration in these two situations? How are they different? We know that we have some acceleration if there are external forces. If there are no external forces, then the derivative of momentum, dp dt, has to be equal to 0. Since the mass can't be 0, this means that in the presence of no external forces, the acceleration of the center of mass of a system has to be equal to 0. If dp dt is 0, then acceleration has to be 0. to get some practice with this concept of center of mass, I suggest looking at example number 9 in your textbook. Now the final thing to discuss is how do we find the total energy of a system of particles. Energy, if we remember, is equal to kinetic plus potential, the two forms of energy that we've talked about. We already know how to find the potential energy of a system of particles. We took care of that previously. How do we find the kinetic energy? We can write the equation. Kinetic energy of a system of particles is the sum of the kinetic energies of each of the little pieces that make up that system. So we have our general equation for kinetic energy, 1/2 mass velocity squared. And we take the masses of the little individual pieces times the velocity of those pieces, and we just add them together. In previous situations when we've done this, we've come up with special equations, special adjustments to these equations that relate to the center of mass. For the purposes of kinetic energy, we don't have such a system that we can do. We don't have such a process. We just have to add up the individual kinetic energies of each of the particles. The total K is just basically the sum of the individual K's. Easy peasy.